All right, class, this is Coach Williams, and we are going to cover 5.4 notes today. The notes that we're going to go over here are not a whole lot of things new that we're going to cover. We're actually just adding to some of the things we already know, and that is we know how to solve systems of equations. We are just going to identify by the answers that we get whether or not we have one solution to the systems of equations, or if we have no solution, or if we have infinitely many solutions. And there's one thing that we're going to learn as we move along here. We really need to understand what parallel lines is so that we can determine if two lines will ever cross, or if we happen to have two lines that are the same slope on top of each other, which in essence are like parallel lines that just end up with the same y-intercept. Obviously, they're crossing the same place. All right, so the first vocabulary term that we have here is parallel. In this case, I'm actually going to make this more specific: parallel lines. And when we're dealing with parallel lines, this may not be a formal definition per se, but this is going to be an identification process that we're going to have. This is going to be lines on the same plane. Lines on the same plane, we'll go into a little detail on that in just a minute, having the same slope. And that's going to be important. We're going to be looking for that as we move along in our equations, having the same slope. And something we may add to that is that they will continue being the same distance apart. In other words, as they move along in one direction or the other, they will continue to be the same distance apart, meaning they will never cross. Or intersect, if you want to write that too. It doesn't matter. They will never cross or intersect. So parallel lines are lines on the same plane having the same slope. They will continue the same distance apart. They will continue being the same distance apart in either direction that they go, meaning that they will never cross or intersect. And that's going to be important as we move along here. The most important key here is this same slope business. Now let me talk about the same plane. When we're talking about the same plane, we can use a wall, we can use the ceiling, we use the floor as a plane, and it just means that, like a flat, surface, we'll say at this point, just kind of so we can see that in our minds, that continues on, infinitely in every direction. And as long as the two lines are on that plane, if they lie on the same plane, in other words, let's use this piece of paper that we have here as a plane. If I have two lines on this plane, and they are parallel, then they will never cross, and they will maintain the same distance apart. They will continue to have the same distance apart in either direction. And now they may be at different angles, or they may incline or decline depending on the way you look at it, but they're on the same plane. Now these are going to be parallel lines on the same plane. If I were to take these two, and if you'll notice, it might be hard to see on the video, but if I were to take them and turn them in different directions. Now these lines right here would still never cross, but they're not on the same plane. So they're not necessarily parallel. So when we're talking about parallel lines at this point in our algebra, this section 5 here, 5.4, we're only dealing with lines that lie on the same plane, and they're going to continue to be in the same, continue in the same direction, having the same slope no matter where I put them. We're not talking about lines that don't intersect, that are not on the same plane like this right here. They would be two different planes. So we're dealing with the same plane here when we're talking about parallel lines. Now, moving on to how we can recognize what type of solution we have arrived at whenever we finish or we are solving our systems of equations. The systems of equations are going to have one of the three options here. One's going to be one solution, which is what we've been finding to this point. At this point, 5.1, 5.2, 5.3 all of the systems of equations we have dealt with end up having one solution. We have two equations, or we have a graph with two lines. They cross, and we have a solution. And that solution is a point that satisfies both equations, makes both equations true. And we've been able to find that by different ways. We found that by graphing. We found that by substitution. And then we've also found that by elimination. And those are the three main ways that we have been solving systems of equations. Now, using these methods, we're going to determine if we're going to have one solution, which is the way we've been, working problems to this point. But then now we're going to be introduced to a possibility of no solution or infinitely many solutions. And so we'll let you know how we're going to find that. In this case, this first one, one solution, we're going to have what we've been finding all along to this point. We're going to have a coordinate or a point where both of these lines cross. And so we're going to have x equal to some value, y equals some value, and we're going to have an ordered pair, x, y, that's going to satisfy both equations. Okay? And so that's what we're looking for when we say we're going to have one solution. Now, what we're going to look at when we have lines that are parallel, these lines don't ever cross. And just as an example here, let's give some value to the y-intercept and the slope of each one of these lines so we can kind of give you an example of what you're going to have as a result when you solve and how you're going to recognize that it's no solution. These lines are parallel, meaning they have the same slope. Let's say that the slope for this first line is 1, just 1 over 1. And let's say it crosses at 1, so that means the y-intercept is going to be 1. So using the formula, or the form y equals mx plus b, the equation for this line using the slope and y-intercept is going to be y equals x plus 1. All right, so just as an example here, we're going to give this an equation. We'll give this other one an equation. Let's say that it crosses at -2. It's not exactly, but just for sake of demonstration here, the slope is still 1. The y-intercept is going to be -2. So if that's the case, then we're going to have an equation that says y equals x minus 2. Now, what do we know about both of these two equations? They have the same slope, so they're parallel. They will never cross. Another thing that's going to happen is they have different y-intercepts, so they're going to be not on top of each other. They're going to be apart from each other, and they'll maintain that distance as they continue in both directions. So these are our two equations. If I were to use substitution, then I would see real quick that if I were to take this expression for y and plug it into the other equation, then I would have x plus 1 equals x minus 2. Substituting in this expression for y here, this would be my resulting equation. And we know that anytime we have the same thing on both sides, when we have this condition like this where x is on both sides, they're just going to cancel out. And so the x's cancel, they go away, and I'm left with 1 equal to a -2. And we know that that's not true. We know that that's not true. We know that 1 does not equal -2. So when we come up with a constant that does not equal another constant, and one of these may end up being a 0, but we're going to end up with two values that do not equal each other, that's when we're going to see no solution. And there's multiple ways we could have approached this problem. We could have done elimination if we wanted to. We still would have ended up with two values that did not equal each other. So when we have a value that does not equal another one, our x and y terms are gone, then this is going to be no solution. All right, on to the next one, infinitely many solutions. Again, this case here, we actually have lines that are the same, or it's a line on top of a line. It has the same y-intercept. It has the same slope. Okay, so we might write that down. We have the same slope. We have the same y-intercept. All right, and when you run into that situation, you're going to have two equations that basically equal each other. And so this is what's going to happen when you do that. Let's give some value to this one again. Let's say that this is at 1. Okay, and let's say our slope is a negative 2. Or negative 3. Negative 2, negative 3, it doesn't matter. We'll just say it's a negative 2. So our slope equals negative 2. Then that means that both equations are going to be y equals negative 2x plus 1. And, you know, you may see this where it's negative, everything's doubled. So it might be 2y equals negative 4x plus 2 if everything's doubled or tripled or something. But in essence, you're going to end up with the same equation if you were to reduce them or to multiply something, you know, to where you end up with the same equations here. You're going to see that that's what it would be. You have the same slopes and the same y-intercepts. Again, just for simplification of demonstration here, I'm going to take that whole thing, I'm going to substitute it in. I'm going to end up with negative 2x plus 1 equals negative 2x plus 1. And what's going to happen here is everything's just going to cancel. And I'm going to have 0 equal to 0. And that's what we're looking for. If we end up with 0 equals 0, we're going to have infinitely many solutions. Okay? Okay, we had a little slight technical glitch there, but what we were saying is these will be the three scenarios that you're going to look for when solving for systems of equations. You're going to look for either being able to find a value for x and y, which means you'll have one solution. Coming up with two values that do not equal each other, so that's no solution. Or 0 equals 0, which just means you're going to have infinitely many solutions. So we're going to look at the following problems and determine which scenario or case we end up with as we move along here solving the following problems in exercises 1 through 18. This is our extra practice number 1. The first thing that I know I can do is just take this whole thing, and we can solve this by substitution like we did in some of the examples above. And that means we're going to take 3x minus 7 and put it in place of y. So 3x minus 7 equals 3x plus 4. And again, we just took 3x minus 7, put it in place of y. We know that 3x and 3x are going to cancel. I'm going to use a different color here. 3x and 3x are going to cancel out. So we have a negative 7 equals 4. And we know negative 7 does not equal 4. So because we have two values that are not equal, then in this case, we're going to have no solution. No solution. All right, number 2. In this case here, we actually could do the substitution. We could take 5x, put it in here. And again, there's multiple ways to solve this. We can do graphing, substitution, elimination, however you want to do this. But I'm going to show this a different version of what we can do here. And elimination is a very common and easy one to do. I could substitute that in, but instead, I could also just add these together and eliminate my x term. If you'll notice here, I've got the same coefficient in front of x, just a positive and a negative version of that. Since the signs are opposite, then I'll add these two equations together. And when I do, y plus y will be 2y. 5x plus a negative 5x will be 0. And then negative 1 plus 5 will be a positive 4. So then 2y equals 4 because the 0 just goes away. I'll divide by 2 on both sides, and y is going to equal 2. Now we've been able to find a value for y, and subsequently we will be able to find a value for x. So this is going to be a situation where we have one solution. But don't stop there, because it said go ahead and solve the system of linear equations. So let's find out what x would be. So if I take 2 and I plug it back into the top equation, I guess. I could use either one, doesn't matter. But 2 instead of y, 2 is going to equal 5x minus 1. So we have our 2 when we need to find x. Plugging it in, we're going to take the negative 1 to the other side. It means it just changes signs. So we're going to add 1 to the other side. And that means we're going to have 3 equal to 5x. I'll divide by 5 on both sides. The 5's will become a 1 and go away. And x is going to equal, yes, it's a fraction, but don't panic, 3/5. So my ordered pair will be 3/5 and 2. And that is the solution that I found for number 2, and it is just one solution. I could plug that into these two equations and it would satisfy both equations. Okay, on to number 3. Number 3, again, I like the way this looks because I've got the same coefficient in front of the x terms, the same one in front of the y terms, and although they're opposite signs, I can eliminate something at least here. I'm going to add these two together because they're opposite signs, and actually both cases are opposite signs. And you can kind of look ahead and see what's going to happen here, but this is going to end up being a 0 plus 0 equal to 0. And since 0 equals 0, then we know that this is going to be infinitely many solutions. And that is our answer for number 3. So they gave us one of each type here. We had a no solution for number 1, one solution for number 2, infinitely many on number 3. Let's flip the page and go to number 4. On number 4, again, I'm going to use a lot of elimination as my method of solving because it just works out, a little easier in many cases, especially for the problems that they gave us because many of them have the same coefficients for the x or the y terms, or maybe both. All right. So in this case right here, again, I'm going to use opposite signs. I'm going to use addition to help me eliminate something. And in this case, it's obviously going to eliminate both terms again. We're going to have a 0 plus 0 because the negative x and positive x is 0. Negative 3y and positive 3y is a 0. But I'm going to have this equal 9 because 6 plus 3 is 9. So 0 is going to equal 9. Is that true? No. So because I have an inequality here, or two values that are not equal to each other, I'm going to have no solution. My two x and y terms have gone away, and I'm left with two constants that do not equal each other. Okay, number 5. We'll switch colors here just for sake of giving you something else to look at. I'm going to again add these together because I have opposite signs. Then 6 and negative 6 will be a 0. 6 and negative 6 will be a 0. Negative and positive 3 will end up being 0. So 0 is going to equal 0. And I'm going to end up with a quick and easy solution here, which actually is infinitely many. So we have no solution and infinitely many solutions. Let's see what number 6 is going to be. Again, it looks like I'm going to end up being able to solve for x because my y terms I can eliminate using an elimination here. I can use addition again because I have opposite signs. So if I add these, I'm going to have 5x. Like we mentioned, my y terms should go away. If I add these together, I should end up with 5. 8 and a negative 3 should equal 5. If I divide both sides by 5, the 0 doesn't affect us now. It goes away. Divide this side by 5. That becomes a 1. So x is going to equal 5 over 5, which is also a 1. I can already write down that I'm going to have one solution because I found a value for x, and now I'm going to go back and find a value for y. I'll plug in 1 to either equation. Doesn't matter. I'll just plug into the top one. 2 times 1 minus 5y equals a negative 3. Now in previous videos, I've done it both ways, but in previous videos I have mentioned, if I'm solving for y, I like to use the positive y term so I don't have to divide by negatives in the end. But to show you that it works both ways, we'll use the top equation here. This will become a 2 minus 5y equals a negative 3. I'm going to move this positive 2 over here, which means I'm going to subtract it from both sides. I end up with negative 5y equals negative 5. Divide by the negative 5 on both sides, and y is going to equal 1 as well. So we're going to have an ordered pair 1, 1 as our solution, and our only solution, so we have just one solution for this system of equations. That is 4, 5, and 6. Let's look at 7, 8, and 9. On 7, 8, and 9, again, I'm going to use a lot of elimination just because it helps me to get through these pretty quickly. I believe it's probably the easier way to do this. If you'll notice again, I've got x terms or coefficients that are the same except for the sign is opposite. Here I've got y terms that are the same. The signs are the same as well, but I'm going to use elimination here to get rid of my x's because I'm just going to add these two together. So that'll be a 0. This will be 6y. And when I add these together, I'm going to end up with a negative 6. Negative 7 plus 1 is a negative 6. And you can see rather quickly here that we're going to end up with a value for y. So this we can go ahead and write down is going to have one solution. And we're going to divide by 6. Divide by 6. Y is going to equal a negative 1. I'm going to take that negative 1, plug it back into one of the equations. I'll just use the top equation. 2x plus 3 times a negative 1 is going to equal 1, because instead of y, I'm going to put the value of y. Then I'll solve for x. This is a negative 3. 2x minus 3 equals 1. I'm going to take that negative 3 across, which means I'm going to add 3 to both sides. So 2x is going to equal 4. Dividing by 2, I find that x equals 2. So my ordered pair will be 2, negative 1. I have one solution on number 7. On number 8 and 9, we're gonna notice something about these two rather quickly. Hopefully, I think you'll notice this right off the bat. What has been done to all of the terms from the first equation? We've taken that first term and we've multiplied it by, in this case, a negative 2, right? But they're just doubled. You know, disregarding the sign for a moment, we just doubled every one of the terms. So, if I were to rewrite this, and this is just kind of helps me get either to an 8 or back to a 4, and I'm going to go back to a 4. So I have the same terms or same coefficient in front of the x variable there, and same coefficient in front of the y variable. If I divided that by 2, divided by 2, divided by 2, then my first equation is 4x plus 3y equals 17. And this second equation, okay, I just rewrote that there. Now the second equation is going to be negative 4x minus 3y equal to 17. And then now I can use elimination to get rid of one, or in this case both, of my variables. So doing that, I'm going to add these together. I'll change colors here. These will be 0. This will be a 0. But 17 plus 17 is a 34. Okay? And so what I end up with is 0 equal to 34. And is that true? No, that is not true. So since that is not true, we have two values that are not equal to each other here. This is going to have no solution. All right, on the last one, number 9, 3x minus 2y equals 6. Again, you can see that something has been done to every term here. Disregarding sign for a moment, and I think actually in this one the sign does matter, but just don't worry about the sign. Just think about the value of each one. We've multiplied by 3, or in this case a negative 3. Multiplied by negative 3. Multiplied by negative 3. And so if I just took and divided by 3, divide by 3, divide by 3. Not worried about the sign at this point. The top equation is 3x minus 2y equals 6. The bottom equation is going to be negative 3x plus 2y equals negative 6. I can take those and add them together and try to eliminate some variables here, variable terms, so I can get down to an answer possibly. I'm going to have a 0 here. This one's going to end up being 0, and that one actually is going to be a 0. So I'm going to have 0 equal to 0, which means I'm going to have infinitely many solutions. Okay, so here we are. We've got one solution, we've got no solution, and we have infinitely many solutions on 7, 8, and 9. All right, the last problem that we have here is a word problem, and it works out pretty nicely as well. You have $15 in savings. Your friend has $25 in savings, and you both start saving $5 per week. All right, so let's write two equations here, and this is going to be me, and then I'll have one for my friend. But me, I started with how much in savings did I start with? $15. And I'm going to put $5 a week. So 5 times every week, $5 times every week, plus the 15 that I started with, it's going to equal, and I'll just put my total savings, we'll say. My total savings. Now, my friend started, he's going to put $5 a week in, but he started with $25. And that's going to equal his or her total savings, right? I have myself and my friend. Squeeze the N in there. 5W plus 15 equals the total savings. 5W plus 25 equals the total savings. What is the slope of both of these equations? They are parallel, as somebody mentioned in class here. They're parallel. They're both 5. So will these ever be the same amount? Same value, total savings in the bank account? Will we ever have the same amount if we continue to put the same amount in every week? No, we're not. These are parallel, so this will have no solution. So my answer is no. And I can say that we are parallel lines. We have the same slope, because we're putting in the same amount of money per week. And yes, we have the same slope. We put in the same amount of money per week, but we have different... Oh, if I could spell different. We have different y-intercepts or starting amounts. Okay, we have different y-intercepts or starting amounts. And because we started at different levels, as long as we continue to put the same amount in per week, we will never reach the same value or same total in our savings. We'll never intersect, we'll never cross, because we have the same slope. Okay, I hope this has helped you guys out. If you've been watching the videos, keep checking back as we move along. We'll try to keep you guys updated on notes videos and practice videos. Hopefully this helps you guys out, and hope you have a great day and enjoy the video. Be sure you work on your practice to get practice on 5.4.